start the recording. And then I have to do this bit. I have to share. Sweet. Okay. So now everybody at home can see what I'm doing as well. And we're going to do this. I'm going to put this here for a second. That's in focus. Beautiful. Okay. So I will try and go through some things that are fun, interesting, and informative. Okay, so the first thing was talking about piecewise functions. And I thought I should do a piecewise function. Who doesn't do that? That sounds like fun. Recording, stop, share, beautiful. What I really want to, I want to put that open there so that I can see what I'm doing. So the people online, it can be difficult for me to see your questions, but I've got the chat open so that I can sort of see questions you post. Feel free to post questions, comments. I will try and address them. And so let's go. So interestingly enough, in the sample exam, first question, do composition of functions for piecewise function. I'm like, oh, right, I can do this. So I thought I would do yes, we change topic. All right, do some things. We should go 1m and we should do 1. All right, so let's go absolute value of x. All right, that's what we're going to call that one f of x for this purpose of this, and we are going to define it as x if x is greater than or equal to 0, and minus x if x is less than 0. Standard definition. You should all see that. That's directly from your notes. So let me define a g. G of x is equal to, and I have thought, what the hell? Looked interesting. X less than 2. And I'm going to say 2x, x greater than or equal to 2. All right. This kind of surprised me. This is me making stuff up, right? So sometimes it does do the thing I want and sometimes it doesn't. So the first thing I did when I did this is I thought, what on earth does that even look like? All right. And so minus x for, so up until this line, sort of x is equal to 2, it's going to be this minus x. And minus x is just a straight line through the origin. All right, so I can go that. Strictly speaking, the way I should do this is I should put a little circle here because it's not equal to 2. And then I should go sort of somewhere up here. It goes like that, and it should be a slope that's greater than that. So that's a little bit about what my sort of y is equal to g of x graph looks like. I want to put that in there because of the complexities in what I'm about to do, it makes it better to have the graph there to see what you're doing. All right, can help you guide what you're going to do. All right, so question said, literally the question from the exam booklet said, find f of g of x. And so the answer is, I'm literally going to put in g of x wherever there is x in f. And so this should be equal to, horrible function, it should be g of x if g of x greater than or equal to 0. And it should be minus g of x if g of x less than or equal to 0. Okay, sure. Well, so I'm going to actually try and interpret this a little bit. G of x greater than or equal to 0. So that is when x less than or equal to 0 or x greater than or equal to 2. All right, so that's why that's quite literally why I have my graph here, because I'm like, g of x greater than or equal to, so that's allowed me to sort of go, all right, greater than or equal to 0. So above or including the x-axis. So I've gone, okay, from here, that's above, this is above. I've got this little bit that's not. So I'm going to go 0 less than x less than 2. All right, so that's kind of telling me my new regions, okay? So then, all right, because we would then want to sort of go, when is it sort of less than, so we've got this horrible thing, less than 0. And so I've got g of x, I want it to be g of x if g of x is less than 0. G of x less than 0 would be this. So if I go, I'm going to have, so x less than or equal to 0, it wants to be g of x. And so if the thing I'm doing g of is less than 0, it should be less than 2. And so I'm going to say minus x. Okay, sure. Sound like a thing. And did that right? Oh, no. No. I did it again, didn't I? G of x is greater than 0. So I want g of x. No, that's right. That's right. Beautiful. I should stop doing this. I have said, yes, I did want minus x there. And then I want 0 less than x less than 2. That's this bit here. So it's minus g of x. All right. And so this is x less than 2. So I'm going to go, it's this bit. So it's minus x. Okay? Sure, that's what it says. This bit says it's minus x from here. And I'm putting it in where there's minus x. Sweet. And so this last one comes from here. So that's where x is greater than or equal to 2. And that's now this bit here. So it should be 2x. Yes, that's the other thing you guys need to remind me about, is the pushing the thing up so that I can, it's always on the screen. Because I will focus on what I'm trying to say, and I will do stupid things like forget to show it on the screen. All right, beautiful. So this is kind of horrible, all right? So, and I had to use my little map of it to work out what's going on. So but I can still work out what any value is, all right? So realistically, if I was to graph this, x less than this, it would be this line. Maybe what I should do is I should go, all right, minus x, x less than or equal to 0, x, 0 less than x less than 2, and 2x, x greater than or equal to 2. So only thing it changes is a little bit down here. All right, sweet. That sounds like a thing. And that sounds like what I expect. Let's try and do the other way around. All right. So the thing in your notes told you quite clearly that g of x, g composed of f, is not equal to f composed of g. G composed of f is not equal to f composed of g. All right. And so one of their favorite pastimes, there are some rare cases where it's going to work. If I'm careful about what I choose, I can go, how can make that happen? Kind of fun and interesting, but nobody cares. So this is going to do the same thing. When I put these around the other way, it's going to be the same thing, except for I'm going to have to shift this up. So now I'm starting with putting f of x into g. It's going to be minus f of x less than 2, and 2 f of x greater than or equal to 2. So, quick digression into what f of x looks like. All right, we all know what f of x looks like. It's a nice thing that comes in here, comes out here. And if I talk about f of x less than 2, all right, sweet. So what's going to happen is this bit here is going to broken into sort of a little bit from -2 to 0 and a little bit from 0 to 2. So when I come to write this out, I have actually tried to keep them in the order that x is in. So I'm going to have x less than or equal to -2, -2 less than x less than 0, 0 less than x less than 2, and x greater than or equal to 2. All right, so I'm breaking it into 4 bits. So because my absolute value thing actually splits at 0, I kind of want to split those into 2 bits as well. I could do it without it, but then I'd have to interpret what f of x is, okay? So if I have f of x less, so if I have x less than or equal to 2, f of x is greater than or equal to 2. So it's this thing. So it's going to be 2, and f of x is going to be minus x in that region. So 2 times minus x. In this region here, that's talking about this little bit here. So now I've got the absolute, so f of x less than 2. So it's going to be minus, and f of x is negative there. And so this is going to be minus x. All right, woohoo, that's a little bit weird, but I'm going to go with it. And so here, this is still minus x, but it's going to be minus x because f of x is now positive. And the last one is going to just be 2x. All right, let's do that again. Let's just write it out again a little bit neater so we can see what's happening. I need to shift that up a little bit. G composed of f of x is equal to, and so I'm going to have minus 2x, x less or equal to minus 2, x minus 2 less than x less than 0, minus x, 0 less than x less than 2, and 2x, x greater than or equal to 2. Sweet. What does this look like? This is kind of a bit weird, this one, and I'm like going, did I do that right? I'm going to try and just give myself a very rough sketch. All right, so one of the things, the reason I'm doing the every so often I do a rough sketch of stuff is I want to sort of go, does it meet what I think? So minus 2x, x less than this. So that's actually going to be a slope of minus 2. So somewhere up around here at 4, it's going to come in like this. All right, x when x is negative. All right, that's actually going to come in from here and go up to here. Okay. And that's going to come down like that bit. So the minus x from there. And then I'm going to come back up here and do this bit in a weird way. So the reason it's got this weird sort of behavior is because if we go back up to what, because g of x has this, when g of x is the guiding function. And so if we imagine g of x for positive numbers, we've got g of x for positive numbers, we've got that bit, but we've got it mirrored as well. And actually, that's what we should have. That's what my graph looks like. So I can go, you know what? That feels about right. Now, I did a thing there. All right, who was paying attention? I did a thing where I go, that feels right, or that, this is, I actually implied that this mirrored the positive part, all right? So the absolute value of x mirrors. So some of the reason we talk about things like functions being even or odd functions is if I know a function is even, it's basically a mirrored in the y-axis. F of x is an example of an even function. All right. So do you remember do we need to go over definition of even functions? Yes, apparently we do. Sweet. That sounds like a great idea. So f of x is equal to f of minus x. All right. But from a geometric point of view, f of x it's actually a reflection in the y-axis. All right. So this is kind of a tricky thing. And so that allows me to go, if I'm doing a composition with an even function, I'm actually going to end up with an even function. All right. So if I do g composed of even function, that g composed of even function actually turns out to be an even function. So, and since we're doing this, we should write odd functions. And that is f of minus x is equal to minus f of x. All right. Now, in the same way as I sort of said, even functions are a reflection of the y-axis, odd functions, if I put my pin in the origin and I turn the graph upside down, 180 degrees, it makes it exactly the same. So the correct way to say that is it's a rotational symmetry around the origin. Okay, so it's a way of thinking about these things that will get you to sort of see what's going on. Okay, did we follow that? All right. Now, having a quick look at the sort of things they did with functions, they talked about, doing composition of functions, evaluating functions at a particular value. Particularly when you have these piecewise functions, doing that evaluation can be a bit of a trick between the two things. So, but it is following a fairly simple pattern. All right. So I could have taken my functions here. All right. I could have taken these and gone, hey, what could I do with these things here? All right. So one of the things they did was okay, I could have created a question which was like g of 3 minus f of 1. All right. And this is just putting in numbers, okay? So if I look at my thing for g of 3, this first one here, we've got g of 3. 3 is greater than 2, and so it should be 2 times 3. So this would be g of 2 times 3 minus f of 1 should just be 1. And so this should work out to be g of 6 minus 1 is equal to, I'm going to say g of 5. And g of 5 follows the same rule, 2 times 5, 2 times 5 is equal to 10. All right, that's going to work. Yes. All right, so I can just put in the numbers. All right. Now, I've tried to do really, really small steps. All right. Really small steps so that I'm articulating what I'm doing at every step. And one of the things I know is my brain doesn't work while I'm trying to give a lecture. So I don't want to do anything that requires actual thinking. All right. So I've made it nice small steps. The same actually applies to you doing the exam. Okay. You don't want to try and do calculations in your head. You want to do them on the page. If I could convince you to do nothing else for the exam, it would be anytime you're trying to even add numbers in your head, write it on the page, write down the answer next to it, okay? You have no idea how much grief that will save you, how much quicker that will make your exam, and how many errors that will reduce, all right? So just by writing out every little thing you know, and the other thing to do, so you remember we did a lot of written assignments and a lot of you came in and said, why did I lose a mark for this? And the answer basically came down to you didn't tell them why you could do that. All right. This is going, hey, I know this. I've even said I'm using this part. So it's making it clear what I'm doing at every step. All right. At no point does the marker have to go, oh, I wonder what he did there. It's very clear. So if every one of your steps is crystal clear, then you will do better. All right. There will not be this, will I lose marks? So the written assignments are actually about training you to do just good mathematical technique. I've got a reason for everything I need to do. All right. There is a clear reason for why I've done it this way, and this is what that is. The other thing I've wanted to do while we're doing this is talking about doing an inverse of a quadratic. And so, inverse of a quadratic, let's do this.
That if you had previous function, say the y function both ways, you get an equal function. Is that the same for all functions as well?
I think it is. I think you can actually show that, couldn't you? Because odd has that property of because it has that property of f of minus x is equal to that. I wonder if, I don't want to do that. That's a really good question. That actually goes a little bit beyond the scope of the course. I love the question. Thank you. Let's just write that down here. Um, no, I want the inner function being. So I want the composition. So is the composition odd if the inner function is odd? All right. Because I think that's the deciding factor. I'm not 100% sure. We could have a crack at it later, but also, like I say, so there are questions like if, actually, before I do that, maybe let's talk about what you would do. What would you do if that was your question? All right. I feel like that would be a bit of a tough question for Maths 1M, but maybe like it's just on the edge of what is possible in the exam. All right. Does anyone have any ideas? All right. I feel like that would be what I would be if I was in your position and I read this question. What should you do? All right. So first thing you should do if you have no idea what to do, put a little circle on the exam paper or make a note somewhere to come back to that question, get everything that you can done right. All right. Exam technique, peoples. Exam technique says do the things you can do first and the things you don't know what to do next and the things you have no idea about you look at last. All right. Get the marks you can get first. Right. But if I'm doing this, the thing I know I need to consider g of f of minus x. All right. Now, I actually know it's not going to work because I can say that's going to be g of minus f of x. All right. But I can't pull that minus outside, so I can't say that this is so. Yeah, I may revisit that. All right, there could be a trick. All right, I'm going to go through and go, man, maybe not. All right, like I say, my IQ drops when I'm giving a presentation. So there may be something I could have said there that I didn't. Okay, so one of the things that a lot of people want to have a problem with is if my f of x is a quadratic, I'm going to keep it relatively simple. Okay, Can anyone tell me what I should do if I'm trying to find the inverse of a quadratic? Look at the domain. Let's have a quick look at this thing here and go, oh man. So this thing has an axis of symmetry at x is equal to -2. It's going to do, I'm going to go something like that, where that number is -7. All right, I need to restrict the domain. I am going to choose -infinity to -2. And I can include -2. All right, that's a great place to start. Let's try and sort of let's go that way. All right, so I'm going to go now. Okay, all well and good. Then next step. All right, the phrase you are looking for is complete the square. All right, so I'm going to write f of x, which we have said is x squared plus 4x minus 7 is equal to x plus 2 all squared minus 7. I've got to take away this number squared as well, minus 4. Now we'll write this as x plus 2 whole squared minus 11. So now I do the standard y is equal to x plus 2 all squared minus 11. And I change the subject of the formula to be x. All right, so I'm going to go y plus 11 is equal to x plus 2 whole squared. And then I take the square root. And at this point in time, I'm going to put in the plus or minus. Move it up. Yep, good work. Is equal to x plus 2. Now, at this point in time, I'm going to go, oh, okay. Now, bearing in mind, my x's are all sort of here in the negative world. So this actually needs to be a negative number. All right. So that's why I can sort of go that extra step and go, all right, my x plus 2 is going to be equal to minus square root of y plus 11. All right, thing under the square root, positive, yay. But the number out front needs to be this. So I'm going to get x is equal to minus 2 minus square root of y plus 11. And so, and this can be interpreted as f inverse of y. All right, so this variable is saying y is actually the variable of this function. All right, so f inverse of, as written as a function of y. So I can just go f inverse as a function of x, basically that, minus 2 minus square root of x plus 11, and just change the variable name. All right, the variable name is like a placeholder. It can change. I can call it Bob if I really wanted to. But it's just something to signify where it belongs in the formula, okay? So it can change. It's really important that we remember simple things. And that, in this case, is that we need to look for functions being one-to-one. So all right. There is a horizontal. Oh, do I? Beautiful, thank you. So we all know the horizontal line test. If I draw a horizontal line, if it cuts more than once, the function is not one-to-one. And then we have, if not one-to-one, then All right. Next on the list of things to do is change the subject of the formula. All right. All right. So that's that bit where I've sort of gone, hey, I've got my formula, y is equal to something in terms of x, and I've rewritten it so x is in something in terms of y. And that's allowed me to say inverse is a function of y, hence inverse as a function of x can be this, all right? Okay, last and very, very, very much not least, state the answer, all right? We give you a lot of questions, all right? Now, the questions are only there so you can demonstrate what material in the course you've understood how to use. But you still have to state the answer, all right? Because that last line is saying, I know this is the answer. If I'd left it here, I probably still would have got full marks, but the marker would have been gone, why didn't you say that? All right? That would have left them with a little nagging doubt that says, I don't know that you do know what you're doing. All right? So I'm not 100% sure. And so that's why you need to be clear about what's going to happen. And the way you do that is you state what you think the answer is. All right? That's the important part of this process. Okay, so yeah, that's our plan. Do the plan. Okay, now, all right, I think, how are we doing with that? Did we want to talk anything more about sort of piecewise inverse functions? Yeah, no, we won't do that. No, we're good. Beautiful. I'm taking that as a no, we're good. Thanks. I'm going to get myself a new page. And so, induction. I like talking about induction. Induction is fun. All right. All right, so let's go through this. First thing we want to do. Formally, this is what we want to do. While I'm writing, sometimes I have to stop talking because I can't do two things at once. And finally, all right. Now, this first bit is one that we don't often talk about. All right, stating the proposition. Strictly speaking, the best way to go about doing this is we want to give a proposition which is dependent on the indexing number, all right? So we want to state a proposition that is dependent on n, usually. Then we want to state the base case. So this is true for n greater than or equal to 3. Everybody loves number 3. So that's where I go, well, if n is equal to 3, this is what happens. And then we can go, hey, we can observe that's a true state. When we're talking about the inductive hypothesis, we want to go, let's assume it's true for some value of k, and show that the inductive hypothesis is true, or the proposition is true for k plus 1. And the conclusion is we go, hey, I showed this base case. I showed that if it's true for some number, it's true for the next number. then by the principle of mathematical induction, I know it's true for all n greater than or equal to the initial case. Now, that last bit is where we're actually using induction, all right? Have a wonderful, wonderful example where a friend managed, it's quite funny. He's like, I don't know if this is true, but I've managed to show the inductive hypothesis. I just need to find the first case. And the answer was, there was no first case. It was not true because there was no first case. And there he was actually going, oh, okay. Because I can't, in the process of trying to find the first case, he was able to show that there was no first case. And so you can have a vacuously true statement. If this is true, then it follows that it's true and the next case is true. But now, the other thing I've got is a really, really old math textbook. But it says principle of mathematical induction, and it's got it divided into a whole lot of things. So number sequences, induction and proposition. So this is actually where we can talk about what they're doing, but then we've got different types. So sum series, divisibility, inequality, recursion. Now, all right. So those four categories can differ ever so slightly in how you go about doing it. All right. So it's not very far into the book. Love these old pages over at our things. Definition, sequence, application, arithmetic, geometric series, beautiful numbers. And so what can we do? We do that. We don't want to do that. We've got some wonderful examples. So I might try a few different cases. What looks like fun? Hang on. Oh, hey, that's weird. Check it. Look at this one. This one, no. Could we do that? That's a bit. Nobody wants to do that. That's fine. I don't know. Do we have a favorite? All right. I feel like we should do something like this one. So what we want to show, so if I go 1 on 1 times by 2 plus 1 on 2 times by 3 plus 1 on 3 times by 4 plus ... plus 1 on n times by n plus 1 is equal to n on n plus 1. I'm looking at this and going, is that really true? I'm loving this. This series will sum to 1, ultimately. So, all right, proposition. Pn. All right, so I've kind of brought this into a sum. I've written it in summation notation. Are we okay with that bit? So this thing here has told me the form of what this should look like. All right. So when I is equal to 1, I had 1 on 1 times by 1 plus 1. When I is equal to 2, I had I times I plus 1. So that's why each one of these terms can be written as 1 on I plus 1. All right. So this is my proposition, that this is equal to this. Now, so P of 1. So P of 1 as a statement is sum from I is equal to 1 to 1 of 1 on I plus 1 is equal to 1 on 1 plus 1. This side here is literally just 1 on 1 times by 1 plus 1, which is very clearly equal to 1 on 1 times 1 plus 1. Under the heading of tell me what I just did, P1 is true. or Pn is true for n equals 1. However you like to do it. Now, next trick, we're going to do the suppose. All right. Suppose Pk is true. I'm a big fan of the following that with that is sum from I is equal to 1 to k of 1 on I plus 1 is equal to k on k plus 1. All right. Now, what I want to do is now I don't want to say what it is, I want to think about it. So we're actually going to say consider. So we're going to go, and I want to consider one side or the other. All right. So of the next case, so I'm going to consider the sum from I is equal to 1 to k plus 1 of 1 on I plus 1. All right. Now, I'm going to forget all about what happened before this, and I'm just going to focus on what this says. And except for I'm going to use the thing that I just supposed I knew what the answer to is. So I'm going to put that bit in. And then I'm going to add the k plus 1 too. So 1 on k plus 1, k plus 1 plus 1, I'm going to say k plus 2. Now I can say something. I can actually go, well, this is going to be equal to k on k plus 1 plus 1 on k plus 1, k plus 2. All right. If I really want to, I can go by assumption. Didn't leave enough room for all the letters. Let's ignore that. Sure. Now, I want to do the mythical magical thing. All right. I've got two fractions. Okay. We love fractions. We've got the sum of a fraction. We've got to create a common denominator. Woohoo, I hear you all going, yeah, of course we do. That sounds like a great thing, Nick. Let's do a common denominator. So this is going to be k times k plus 2 on k plus 1, k plus 2 plus 1 on k plus 1, k plus 2, which is going to be equal to something. Don't know yet. K plus 1, k plus 2. So it's going to be, I'm going to say k squared plus 2k plus 1. I'm going to try and squeeze this in at the bottom of the page. No, actually, I won't. That won't work. It won't work. So, did we lose it off the bottom of the page?
Every single one of those on the line. On everyone.
On everyone. Shh. All right. Shh. Ideally, see, this is those things when I say, you know what, when you're up the front of a class and presenting, your brain doesn't do all the things it's like trying to do because you're trying to go, hey, am I taking too long? Am I being boring? Have I forgotten to do something? Is my fly open? Whatever. All right. You know, yeah, I've done enough lectures that there was one where my fly was open. It's fine. Nothing worse than getting out of the lecture and going, fly's open. I wonder how long that's been that way. Let's not worry about it now. Sure. At least there wasn't recording of that lecture, so we're all happy about that. All right. Root. Now, we are supposed to recognize stuff, right? This thing here is going to be k plus 1 all squared on k plus 1, k plus 2, which I can just write as k plus 1 on k plus 2. All right. So Now, this is where we can do a little bit of a, hey, what did I just show? All right, this can be like play school. We have just shown Big Ted is in this roundhouse. So we're gonna state the bleeding obvious, all right? Because you've just done it. See it right here. We've shown that sum to k plus 1, starting at I is equal to 1 of 1 on I plus 1 is equal to k plus 1 on k plus 2. So p of k plus 1 is true. We did make an assumption, so I have to go if pk is true. This is I've shown the inductive hypothesis, right? I've shown that the next case follows. If I can find one place where it's true, then the next case must be true based on that fact. All right. And so now, as P1 is true, and P of k plus 1 is true if pk is true. All right. We have stated the answer, all right? So what we're able to do is we were able to bring all of this together and go, hey, I've shown Pn is true for all n greater than or equal to 0. Notice how I've kind of got a little bit uptight about this, and I've spelled it right out, okay? That is because I had a really, really annoying year 12 teacher. If you didn't put on all those words, you would lose a mark. Pissed me right off. But ignoring some minor pettiness that after 30 years we haven't got over it, no. So it's a good idea to put in all of those words, right? It's actually really good to go, this is exactly what I'm doing. So you know the purpose of every one of those things that you've said, okay? So, all right, now, I'm actually going to try and do another one, all right? I know this is a little bit tedious and boring, but you know how I said there were ones that were different? One of those things, so some are series, one thing, inequalities. Now, I'm going to try and do, I don't know, going to try and do something simple. Going to try for something simple. Oh, hey, if n greater than or equal to 1, h to the power n greater than n cubed. Sure, going to go with it. I feel like that's kind of a thing. So I'm going to go through that whole process, right? Proposition. That's what my proposition is. Sweet. Base case. All right. We could actually call these things on the sidelines flags, signposts, telling you what I'm going to do. Tell the person what you're going to do or what you are doing with what you're writing on the page. Because if you go, hey, this is what I'm trying to do, then they will go, oh, that's a sensible thing to do. You should do that. If it's not a sensible thing to do, they will go, I wonder why you're doing that. All right. The marker does know what you're trying, will be able to work out if you know what you're doing, all right? You shouldn't go, I shouldn't write down what I'm doing because that way he may not realize that I don't know what I'm doing. They've figured it out, all right? Not all of the people who mark exams are geniuses. I've marked a lot of exams, not a genius. But also, don't think there's been a single person who's tried to bluff their way through who was successful. Because you go, that didn't do what you said it did. I'm going to just go, you don't know what you're talking about. So don't tell me you know what you're talking about if you don't. Tell me you don't know what you're talking about or you're not sure about it. Sure, I will take that on board and go, yes, but it is the right thing to do. So well done. All right, I will know where you are. Base case, b of 1, which is equal to 8, which tells me 8 to the power 1 is greater than 1 to the power 3, is true. If I really wanted to, I could go by observation. If I really have to spell out why I think it is, 8 is greater than 1, I'm done, right? Can do that. Okay, now, interestingly enough, love these books, right? One of the things I love about these books is see they've coloured in this bit that says, ooh, note, to prove that A is greater than or equal to B, often a good approach is to show that A minus B is greater than or equal to 0. Sleep, all right. Maybe. So let's going to go assume PK is true. And that would be 8 to the power K is greater than K cubed. Sweet. All right. I'm a little bit stuck at this point in time. I'm going, I don't know what I'm going to do. So I'm going to rewrite this and say 8 to the power K minus K cubed greater than 0. Now, I want to try and get to the next case, all right? This is what happens when you don't rehearse stuff. You go, I don't know what to do. I feel like maybe I times through by 8. Sound like a thing? I don't know. Let's give it a go. So if I take 8 times by 8 to the power K minus K cubed, that's going to be greater than 0 because I times by a positive number. I'm happy with that. 8 to the power K minus 8 times K cubed, greater than 0. Now, ideally, oops, that should be plus 1. Ideally, I want to replace this by K plus 1. All right. That's going to be a bit of a trick. So, have I got any plans? No.
You don't know what to do here?
Oh, no, I'm like, would you like to tell me, Mark?
8 is.
Yeah. So I can write this as, yes, that's minus. So I can actually do this. All right. And so that's going to be greater than 0. And so now, K greater than or equal to 1, 2K is greater than K plus 1. No. So the plus, yes. 8 times 8 to the K plus 8 to the 8K cubed. That extra 8 added 1 to the power. Yep, slick. Now, and so I can then go 2 to the K cubed greater than K plus 1 cubed. All right, so this observation here is actually kind of important. There was a trick. All right, thank you for pointing that out for me, Mark, because I was like, oh, when I read the question, I thought, oh, yes, that's going to work fine. And then I was like, what was that thing again? Yes, even I forgot what the trick was under pressure. But this is going to allow me to go, hey, this thing here, like, I'm actually going to say this thing is greater, this is greater than, so 8 to the k plus 1 minus, actually, no, I can't, I'm not going to do that. I'm just going to, because I'm replacing this by something that's smaller than it, all right, I'm just going to go minus k plus 1 cubed. Because I'm replacing it with something that is smaller than it, I'm going to still make sure that's greater than 0, all right? In actual fact, I could say more than that if I really tried, but I don't want to. I just need that. And so that's going to allow me to go that 8 to the power k is greater than k plus 1. K plus 1 cubed. All right, sweet. Loving that. Yeah. So, and then we go, that is, if pk is true, pk plus 1 is true. And then we jump to the next page. Sweet, come on. And 1.6. And so since P1 is true and P of k plus 1 is true when pk is true, then Pn is true for all n greater or equal to 1 by principle of mathematical induction. I am pretty sure your lecturer said, rather than saying principle of mathematical induction, longhand, you can go PMI. All right. So if the question was that, now this is where I go, actually that question would be considered a little difficult for you, for where you are, but it is completely reasonable as an exam question. All right. So it would be considered a harder question, all right, because there was a trick, there was a genuine trick, but doing induction on inequalities and what was the other one? I can't remember. So they do things. The other thing you possibly did talk about was the difference between what's known as weak induction and strong induction. So strong induction, where I assume just, so you noticed I assumed just pk is true. If I have to assume pk is true for all k, for every value of k less than or equal to k, sort of thing, that's what we call weak induction, because I've had to make a much bigger assumption. All right, it still follows. The principle of mathematical induction will still work. All right, did I get it? I'm pretty sure it's that way around. Oh, will we assume all the previous cases? Well, I don't know. I have to look. Possibly. Let's go with that. But nobody. It mentioned what?
I think for the trick part, also would want you to do induction on that part just to show that thing is true.
I think you can actually, well, it's a bit of a dodgy thing where we go 2k is greater than or equal to k plus 1 for k greater than 1. K doesn't even need to be an integer in that situation for it to be true. So maybe not. Anyway, we're not going to worry. We're going to go, hey, that was a bit trickier, and so this is a good example of as tricky as it gets. If you do not know what to do, write out. There was like I got to 1 point, which was very near the end of that question, and if that question was worth 4 marks, I would have got 2 marks if I'd stopped. If I'd got to here and I'd stopped and gone, I don't know what to do, right? Then I still would have got half the marks for that question. I would have still got a passing grade for that question without solving it. And this is actually one of those things that I want to sort of instill in you is write down what you can do, right? If you can't do the question, don't stop writing it. write out the first few steps. Because one of the other things that will happen is once you've written the first two steps, the next step will become a bit more obvious. May not be obvious enough for you to see it in the exam. You can be walking home, walking to the car after the exam and go, oh, fuck, okay. I should have done that, shouldn't I? Not saying it's happened, but I'm just, as an example, saying. So it's really important for you to remember to write down as much as you can, and that will get you marks, all right? You never know if you've done enough of the part of the question to get the mark, all right? Sometimes you're just short of the point where you need to get a mark, but quite often you are a little bit beyond it. And so having done that much, you can write that question. So, all right, one hour in. Now, the next thing that was big on the list of things to do, parametric curves. Parametric functions. I wonder if my book has anything on parametric functions. Oh, book with parametric functions, that would be fun. I don't think it's great. Differential equations, different conic sections. No. Sure, that would work with more else. Let's check the new book. New book. All right. Oh no. What parametric curves do we need to know about? Functions, yeah. Oh no. What's a parametric function that we could have? All right, I am going to go. So we're going to do this in two ways first. We are going to go we're going to do the nice x as a function of t and y as a function of t. I wonder what we can do. Let's try and do something a little bit weird and go like t squared plus 3t minus 4. And let's go sine of t. Yes, yes. All right. Sweet. I have no idea. But what do they get you to do with parametric curves? Why do we care about parametric curves? All right. So the thing you were told about parametric curves, all right? So let's see, we're going to go dy on dx is equal to dy with respect to t divided by dx with respect to t. Yeah? Sound like a thing. But they then said dy on dx is 0 if dy on dt is equal to 0 and dx on dt not equal to 0. All right. Similarly, we said dy on dx is undefined. If dy on dt not equal to 0 and dx on dt equal to 0. All right, so divided by 0. Roughly speaking, this one is horizontal. All right. This condition here means that it is still moving up, where it's not moving across. Vice versa, this is not moving up, but still moving across. Now, one last and wonderful case. Now, what did they say? I forget what the notes said. Forget the term they used. So if I have both of those derivatives equal to zero, so time derivative is equal to zero, then my point is actually stationary. All right, it stopped. If I was a little bit clever about this, I could have actually organized that to happen. Anyway. No, not worth it. What they can ask you to do is actually talk about where the derivative is zero, where the derivative is undefined, and where, like I say, I can't remember the word they used for it, but they had something around here where so 0 divided by 0. So so the thing we want to do is the thing is going to be ask you to do a couple of things. All right, let's think about what you could be asked to do. All right, so find t such that so dy on dt dx is equal to 0, dy on dx is undefined. Sure, that sounds like a great plan. And now, this is going to be the same process for all of these ones, regardless of which one I'm trying to work out. Because I'm talking about this derivative, I need to calculate both derivatives. So the derivative of x with respect to t. So I'm going to go derivative of x with respect to t, nice and easy, 2t plus 3. dy with respect to t is going to just be cosine of t. Right, sound like a thing. All right. So let's do a little bit where we go dx on dt equals 0 when t is equal to minus 3 on 2. All right. And dy on dt equal to 0 when t is equal to, I'm going to say pi on 2 or 3 pi on 2. And so I could write this as pi on 2 plus n pi. And I would go n is an integer. I meant to do that. N is in the set of integers. All right. So if we go back up to what we're trying to do, it's equal to 0 whenever the dy dt is equal to 0. All right, sure. So dy on dx equals 0 when t equals pi on 2 plus n pi. N is in the set of integers. We read the nice, so we read it as in, but it is in, and this is the set of integers. All right. dy on dx is okay. Now, so at t is equal to minus 3 on 2, the particle is traveling, this thing describes vertical motion. For all these nice periodic values, the thing stops. The thing is effectively stopped. What this means, though, is I could actually create a function that would give me the tangent, couldn't I? Yep. So find t is equal to 1. Sure. I don't want to make it difficult, or maybe it might be difficult. Did I have done button no? Oh, no, do that. Actually, I think what I'll do is I'll make this pi on 4. That works better. Pi on 4, yes, it sounds like a thing. And so x pi on 4 is a horrible number. It's like pi on 4 squared plus 3 times pi on 4 minus 4. This number is less than 1, so it's not terribly big. This number is about 1.5, 2. Yeah, I'm going to say it's about 2, 2.5. So this number is slightly negative. Less than 0. Horrible number. Why pi on 4? Why pi on 4? Where was I? Sine, which is equal to sine pi on 4, which is going to be equal to 1 on root 2. I prefer to use 1 on root 2 for that. This is the point that it goes through. Digress for a trick. All right, so let's stop sharing there. Let's go sweet. I'm just going to add a new page. All right, and so we're going to zoom in. So when I want to do these things, sometimes I actually just get Excel. And so I go 5 on 4 power 2 plus 3 times 5 on 4 minus 4. Sure, yeah, do that. Oh, dodgy keyboard. Minus 1. I'm going to call that number minus 1. So I should do minus 1.0. Let's say 27. And then I'm going to 1 on root 2. Okay, so we know it goes through that point. dy on dx, and we're going to go t is equal to pi on 4. Is equal to, what did I say the thing was? So I've got where did I put my x derivative? X derivative is this, so this should be cos of pi on 4. Cos of pi on 4 divided by 2 times pi on 4 plus 3, which will be equal to 1 on root 2 divided by, I don't know, pi on 2 plus 3. Bleh, horrible number. I might actually simplify that down a little bit. Can I simplify that down? Maybe. I can write that as 1 on root 2 by pi on 2. Whoops. Zoom with that one. And then I go share that one. Sweet. Pi on 2 plus 3. Okay, sure. Good, loving it. Sweet. And then, so I've got my slope. So I'm going to go y is equal to slope 1 on root 2 pi on 2 plus 3 times by x. And if I do x minus x value, well, x, so that would be plus 1.027. I could actually write it like this. There's a dodgy trick where I can sort of do, so we might just, where's that one? This is using a form which is like f dashed at sort of x naught, and then x minus x naught plus f of x naught. This is a form you can use to sort of bypass having to do horrible calculations. I don't really want to do horrible calculations because they suck. All right. So what are they going to ask you about? So let's recap what we could possibly get asked about if we're talking about parametric functions. So one of the first things they're going to do, right? So bear in mind, right? Lecturers get judged on how many students pass their course, right? So actually, kind of a dodgy thing is like, it's actually, if I'm the lecturer, it's in my best interest to make sure people pass. Sadly, the university has standards. I know you wouldn't think that, but no, there is standards that you have to meet to pass the course. So what they're going to do is they're going to put in some questions that everybody should be able to do. So there's nothing in this question that they wouldn't expect a student who is prepared to pass the course cannot do. All right. So that question on induction, an average student should have been able to get half marks for that. A good student should have been able to get full marks for that. And so the student that should pass, this course, this is a bit messy, all right? Because the numbers are a bit messy, that adds a degree of difficulty to it, right? But there is two things that are doing in here, all right? So one of these things is calculating a function value, all right? You do not need this. I could have left the number looking something like this, and for an exam, that would have been acceptable. All right, so this expression for an exam is the exact value, and so it is acceptable in the exam. All right, because I want to work with it a little bit, you should have a scientific calculator. You should be able to work out what that number is correctly. All right, and then you should be able to give me a statement like this for the expression of the tangent line at a particular point. So finding a point for a particular value of t, finding the derivative for a particular value of t are two things that we would expect you to be able to do. Combining that into the equation of a tangent, we'd expect you to be able to do that. Telling me where the function is undefined or where the function is, so they may use the phrase, so they may actually talk about it in terms of a particle, the motion of a particle, and so where the function is traveling vertically, where the particle is traveling horizontally, and where the particle is stationary. So all of those things you should be able to do. All right? Should be able to do without any difficulty. If you can do those things, bear in mind, so I picked on functions very much like what they would give you, all right? So polynomial, trig function, exponential function, say, is another example of something, exponential log, all those things that have a relatively simple derivative. It's an example. I don't want you to do fancy circus tricks. I want you to demonstrate understanding of what we've told you. So this thing here where we're talking about there we go, give it a second. Where I've talked about the various cases, all right, that's an example of you demonstrating that you knew what I've told you, all right? So if you write that out, go, hey, that's what I'm looking for. If you make a mistake somewhere along there is room for them to give you marks, okay? So it's important you put down, hey, you said you want it where the derivative is horizontal. That means I need these two conditions. If you got that bit wrong, they can go, hey, you were looking for the wrong thing. That's why you got it wrong. It's better for them to know why you got it wrong, because sometimes they can go, but you did the right thing based on that, so I can give you marks for it. If you just go here and you go, I don't know why you did that, it makes no sense. All right, then I haven't got any reason to give you a mark. I'm sorry, but if you said you've made the wrong assumption, then I have reasons to give you marks. Okay, questions? No, cool. So that's about the most of what you're going to get with parametric curves, all right? They're not fun, but in actual fact, if we come to raw drawing with that, where you're going to use parameterization is in integration, multivariable integration. I have a path. All right. I'm going to say that's 4. I'm going to put in this point is 1 and 3. I'm going to call this point 3 and 3, and this is going to be 3 and 1. All right. Okay, so I'm not sure if you actually have to create parameterizations. All right. How would I create a parameterization? If I want to go along this path from here to here, all right, then we call this P1. So where you're going to use this is you're going to do a thing where you go, my P1 is a path. So how I do this is I'm going to do a thing where I have the point. So I'm going to go 3, 1 plus t by 0, 2, or 3, 3 minus 3, 1. And so I can rewrite that as 3 and 1 plus 2t. And that would be a way of parameterizing just the path from here to here. All right. It has a direction. And so just knowing that this is why we're teaching you to do this. There are more complicated paths, right? Way more complicated paths. But a lot of them are really, really simple. Let's do the vector form of a line. Hang on. What did I just say? This is doing the vector form of a line, okay? So I have a start point, I have a direction I'm going in, all right? So quite often when we're talking about a vector form of a line, is point plus t times pq, the direction vector, all right? And if we think about it as that way, so this would be my P and this would be my Q, then this is what I'm doing. So some of that stuff we do, so we did calculus to our parametric form. The next thing we could do is actually talking about from a geometric point of view, all right? And so I could actually go through, now there was some interest in doing sort of parametric curves of lines and planes. All right, so this would be where we come into doing parametric forms of lines and planes. Okay, so where am I up to with time? 3:30, I've got like about half an hour basically. Okay. I'm going to pause momentarily and go, okay. I'm actually going to have to think a little bit about what I would see in terms of sort of equations of lines and planes in a Maths 1M exam. So one of the things I did do is print out the sample exam you have. So I've got a bit of an idea of what sort of questions you might get faced with. Because I did teach Maths 1M a very, very long time ago. All right. So when we talked about parametric forms of lines, so we kind of had lines in three different ways. All right, we had a parametric form. That is where I've got a variable t. So the variable t represents the parameter. That's why we call it a parametric form. The vector form and the parametric form are more or less the same thing. All right, one's expressed as, vector plus t times vector, and the other one is just where I've got t for each of the components. The Cartesian is the one where it's actually a little bit more nuanced about which way we go about doing it. What could we do? What would be a fun exercise? I think I kind of accidentally did some of this. You can see where I've actually got my vector form of my line here, and I've written it in parametric form here. This would be a less fun line in Cartesian form. All right. Because that would actually, I'm not don't want to do that because I think that's something that avoid. In terms of Cartesian form, there are some things. There is an argument that says that you should not that some things are a little bit too much to cover. Okay, so possibly we should try and do this in 3 dimensions. All right, let's consider. I don't know, what's a good A? Everybody loves 1, 2, 3. Trust me. And let's consider a B. I don't know. I feel like I should have a 1, -1. I'm going to go 1. And I don't know. Let's do that. Sure. That sounds like a thing. All right. So now, if I want a Cartesian form, so there's a little bit of there's a talk. The talk goes, different forms highlight different aspects of things and make certain things easier, all right? So my parametric form is something I want when I'm trying to do an integral along that line, all right? So when I've got multivariable functions, which you will get to if you get to sort of secondary math stuff, you want to be able to parameterize a line, because what you're going to do is you're going to take a 2 or 3 dimensional path and convert it into a function of a single variable. And once it's a function of a single variable, you can do an integral along it nice and easily, right? That sounds like a thing, doesn't it? To me, that sounds like a thing. All right, and so part of me is going, I'm not actually sure why I'd want to put it in Cartesian form, other than I can do it. So, hey, whatever. Possibly if I know a particular x value that allows me to sort of solve for y and z in terms of that x value, but I can't actually think of another reason why I'd want to do it that way. But hey, so different forms. So a better example of what I mean by different forms, like when I'm talking about a quadratic, I have a general form, and so general form ax squared plus bx plus c. C tells me the y-intercept, the a tells me which way it opens and how steep it is. But then I can complete the square on it, and that form tells me what the vertex is. All right, so it highlights the vertex. And if I put it in factored form, it tells me the zeros of that quadratic. So different things, different forms are useful for their own right. So, and you would have seen that in complex numbers, where you saw that, the Cartesian form, where I've got real number plus I times complex number, a real and imaginary part, is good for adding and subtracting and just sort of visualizing what these values are. But when it comes to doing things like multiplication and powers of complex numbers, the polar form is much more useful for. All right. So transforming it into the form you want can actually help you. And so part of this idea is I want to be able to transform easily between the forms. All right. If I have more than one form for a particular thing, I want to know how to get from this form to that form and back again. All right. First thing a mathematician will do if he comes up with a new idea is go, particularly if it's taking something from here to here, the question is, can I go back? All right. You know, it's like if you're taking something apart, can I put it in? Is there a step where I can't put it back together again? Right? Do I want to do a step where I can't put it back together again? So all of this is about trying to go, hey, where am I going to go? All right. So I kind of said before that I should be able to do my parametric form of the line is equal to A plus T times the direction vector AB. All right. We should do AB. The direction vector AB is always defined as B minus A, which is equal to minus 1, 1, 1, minus 1, 2, 3, which will be minus 1, minus 1, it will be minus 2. 1 minus 2 is going to be minus 1. 1 minus 3 is going to be minus 2. Could have chosen those numbers to be positive, couldn't I? Didn't think about it like that, but you know, hey, let's go. And so my line is going to be 1, 2, 3 plus t by minus 2, minus 1, minus 2. Now, this, if I think about this as point plus t times by t by a direction. This kind of lets you in on a bit of a secret, right? If I've got a vector as a direction, I can multiply it by a scalar because it's not changing the direction. It will change the size and it will possibly change whether it's pointing that way or that way. But, so I could, this would be equal to, this line would be equal to 1, 2, 3 plus t by 2, 1, 2. Those are the same line. Hell, if I really wanted to, because I know it's going to go through B, I could go minus 1, 1, 1, and go plus t by 2, 1, 2. And so we've got different ways to write the line. All right, there's lots of different ways I can write a line in a vector form or a parametric form. All right. Now, so does that bode well for what we're about to do? So this is the vector form, parametric form. Okay, vector form, parametric form. This is going to be as simple as writing this as a vector. So minus 1 plus 2t. 1 plus t, 1 plus 2t. Or I could go x is equal to minus 1 plus 2t, y is equal to 1 plus t, z is equal to 1 plus 2t. All right. I want this form. Whoops. Paying attention here. I want this form because this is the form that will allow me to convert it to Cartesian form most easily. All right. So to convert to Cartesian form, I want to get t is equal to for each one of these things. So I'm going to go x plus 1 is equal to 2t. And so t is equal to x minus x plus 1 on 2. This is going to be y minus 1 is equal to t, or t is equal to y minus 1. And this is going to be z minus 1 is equal to 2t. So t is equal to z minus 1 on 2. So my Cartesian form should be that x plus 1 on 2 is equal to y minus 1, which is equal to z minus 1 on 2. You know how I said up here, I could actually multiply through by a constant. Maybe what I'm going to do is I'm going to go back a step and make that constant just a half. So my line would then become 1, 2, 3 plus t by -1 minus a half minus 1. And so that would mean my x would be equal to 1 minus t, y would be equal to 2 minus t on 2, z is equal to 3 minus t. And yep. And so, there we go, beautiful. And so if I go through the same process, t is going to be equal to 1 minus x. I'm going to have minus t on 2 is equal to y minus 2. And so t is going to be equal to 2 minus y times by 2. Okay, sure, I can do that. And here I'm going to have t is equal to 3 minus z. And so, same way as I had this, I've now got 1 minus x is equal to, I'm going to expand this out and just say 4 minus 2y. And is equal to 3 minus z. Okay. This doesn't look anything like this, does it? All right. Now, so one of the points about this is particularly with lines in 3 dimensions, there is no single one way to do it, all right? If you think about lines in 2 dimensions, we've got a really slope intercept form of a line that we're pretty locked into. We could actually do like a more general form, like, 2x plus 3y is equal to some number, 7, and we can have what I call a general form of a line. But when we get to higher dimensions, and particularly transitioning between vector forms and parametric forms and Cartesian forms, the same line could look quite different. Okay, and so that's when we go, hey, would it work if I did this? All right, if I converted it back to a vector form, can I find that point? If I take the point on this line, will it be a point on this line? Can I find the direction of this line and make it equal to the direction of this line? So actually, what can be a really difficult question is, are these 2 lines the same thing? Okay, they don't ever ask that in the exam, but that actually would be quite a fun question. All right, there's reasons I don't send exams anymore. Okay, there is people looking suspiciously like they'd rather go somewhere else right now. And so I think at this point in time, I'm going to pause. This is that bit where I go, I'm going to pause and let people quietly escape. If you have more questions, and I should check, nope, there's nothing in the chat. Nothing in the chat. If there's no more questions, I will go, but I'll give people a couple of minutes to quietly leave if they want to leave. And then if people have got more questions, we can either talk about them to the whole group, or everything will be put online. It will probably, actually David's pretty good, he will probably do it on Saturday, despite the fact that he's not supposed to work on a Saturday. Okay, so do you guys, is there anything else you'd like me to talk about? No.
Maybe.
Okay, what would you like me to tell you about trig functions? Right, I'm going to do it. I'm going to do a couple of things, all right? Okay. So, that was page 8, and I dropped it on the floor. Good work. The reason we number these is that we do this. Okay. So, You guys have now done de Moivre's theorem, all right? Yes. And so if I did Z1 was equal to cis theta and Z2 was equal to cis phi, you would know that Z1 times Z2 would be cis of theta plus phi. All right, I'm going to expand this out. This is cosine of theta plus phi plus I sine theta plus phi. So the real part is cos of theta plus phi, cos of the sum of angles. And the imaginary part is this. I could actually do this. This would be cos theta plus I sine theta times by cos of phi plus I sine of phi. All right, so I've got a cos theta, cos phi. So the real parts and the other real part is going to come by doing I sine theta times I sine phi, which is going to be the I squared is going to be -1. So I'm going to have sine of theta sine of phi plus I by this one, cos of theta sine of phi plus cos of phi sine of theta. And so this is telling me cos of theta plus phi is equal to cos of theta cos of phi minus sine of theta sine of phi. And sine of theta plus phi is equal to cos of theta sine of phi plus cos of phi sine of theta. Notice how for each one of these things I had both angles represented. So there was like something times something plus minus something times something. All right. So that means I can do cos of 2 theta is going to be equal to cos squared theta minus sine squared theta. And sine of 2 theta is equal to 2 cos theta sine theta. Right. Gonna be honest, right? I remember this. All right. But then I know if I had theta plus phi, then this is a cos times a cos, so it's going to be a cos theta times cos phi, and this is going to be a sine theta times a sine phi. Similarly, this is a cos theta cos sine phi and a cos phi sine theta because there's two different bits of it. So I kind of remember this, but I know how to expand it out into this. So I know the trick. All right. So that is the first thing I say you need to remember. All right. And this trick with de Moivre's theorem, great. Everybody love it. You could use it to work out what sine of 3 theta is or sine of 3 phi, cos of 3 phi. You could work out, I could literally go, you know, I could get you to do that. All right. Nobody's done that in an exam to my knowledge. And again, there's a reason I don't set exams. But what would you do? Well, you would go, all right, z is equal to cis theta, z cubed is equal to cis 3 theta, and then equate your real and imaginary parts. And the real part would give you cos of 3 theta. Woo. All right, I don't want to do that. That will be tedious and it's not very instructive. Okay. So while there are some fun things to do, and I'm all down for doing fun things, Some fun things are not going to make your life better. So we don't do them. But you could, it is possible. All right. So there, with knowing complex numbers and understanding Polar's form and De Moivre's theorem and how you can interchange between those two things, you can actually derive any theorems. But I said, for some reason or other, I remember these two, and I just kind of got in my head, I can go from that to that. All right, I can do it. Everybody love it. Nobody's upset with it. But I also remember that sine of theta is equal to sine of pi minus theta. And cos of theta is equal to cos of minus theta. Kind of remember these things because these are the way I get other answers. All right. So if I gave you, well, what's a fun one? Let's do it. Let's do something that may or may not work. If I do like sine squared theta minus sine theta plus 1 is equal to 0, what do you know? What are you going to do? Can you find theta? Now, my answer for this is going to have to be in terms of arc sine of something or other, right? I haven't bothered to think about how to make this nice so that I can get numbers that you could actually do the arc sine of. What do you see? Why on earth do I think you could do this? This is a quadratic in sine theta. So if I say let y equal sine theta, this is y squared minus y plus 1 is equal to 0. And so y is equal to 1 plus or minus square root of 1 minus 4 times 1 times 1. You know what? I don't really want to do that. So we're going to change that. Okay, so that I can make this minus 1 here. All right, because that's just going to allow me to do this. All right, so I'm going to get 1 plus or minus square root of 5 on 2. All right. There's a little thing, all right? So sometimes this is what I mean when I make up something, I start like, you go, oh, that's not right, let's not do that. That's way more complicated. I need those. So because it was about to lead me to imaginary numbers, sine is not an imaginary number. We don't want to go there. I want it to be real numbers. Hey, I've rejigged it to be real numbers. So I'm going to go sine of theta is equal to 1 plus root 5 on 2. Is that possible? One plus root 5 on 2 is approximately 1.6. I think it's 1.61, in fact. All right, well, that's not a problem. Sine theta is equal to 1 minus root 5 on 2. And that number, I don't know, pause momentarily. I have this feeling it should be about 0.6, but I'm going to just do a quick check. I'm going to go equals, do some brackets, 1 minus sqrt 5. We minus 0.6 is equal to minus 0.618. Minus 0.62. All right. 0 point. Yes, that will work better. So I can do this, all right? Is equal to a sine that number. I'm pretty sure that's going to work. Woohoo! All right, so therefore, theta is equal to arc. Whoops. Let's just check. Which one am I sharing? Oh, I've got that one. Okay, so let's go there. Go zoom. Go that one. Nope. Need to go to that one. Beautiful. Hopefully I've got this here. And so arc sine. Oops, a little bit further up. Arc sine of minus 0.618. And I'm going to go with Excel telling me that that is at minus 0.66. I'm going to leave it there because I can't remember what the other digits were. And so this is where I now employ, there is two possible answers. So for a principal argument, this would be a principal argument. Ooh, cha-ching. All right, but for a principal argument, all right, there should be two, right? And so I'm going to use my thing here. Where did I write it? I wrote it here somewhere. So, this one. So I'm actually going to go, so the other value should actually be pi minus theta, which will be pi minus pi plus 0.66. Now, because this was minus something, this value is actually greater than pi. So I could actually do a thing where I go 0.66 minus pi. Basically that number minus 2 pi. Okay, all right. Now, the last thing on the things that, the painful things they can get you to do with trig functions, painful things with trig functions. So, we're up to page 10, 1m. So, I don't know, cosec of theta is equal to 2. Fine. Tan theta. All right. So this one on cos of theta is equal to 2. Therefore, cos theta is equal to a half. Cos squared theta plus sine squared theta is equal to 1. So I have a half squared plus sine squared theta is equal to 1. Sine squared theta is equal to 3 on 4. And so sine theta is equal to, I'm going to go root 3 on 4, on 2, root 3 on 2. And I'm going to whack in a plus or minus. All right. And so therefore I can go tan theta, this thing, I'm going to go is equal to root 3 on 2 divided by a half, or minus root 3 on 2 divided by a half. Yes, divided by a half. And this one, come on, let's do that. There we go. This one here just boils down to root 3 or minus root 3. Hashtag other information that will tell you whether theta should be, which quadrant theta is in, and hence whether it should be plus or minus. Okay? That's about the worst thing that's going to happen using trig identities. The other one is that angle addition formula, so finding the exact value of sine of like pi on 8 or something or other. But we've done that enough times, hopefully. Okay, I'm going to stop here because it is a bit after 4 o'clock. Thank you so much for actually turning up. Makes my life a lot easier to have people here. Yes, you don't have to applaud, that's just. But yes, I appreciate it. Thank you for those people online. We're going to finish it here. Everything should appear on the Math Learning Center website. For those of you who don't know, so if you go adelaide.edu.au and then go Maths Learning, and then if you go resources, there will be a link. There will be a thing where you can go to Maths 1M, click on that, and that will show you where revision seminars. And this one should appear there sometime. Thanks so much for listening. See you next time. There we go.